Hi, my name is Yuris. I am the application engineer at CENOS, the affordable platform for engineering simulation. We integrate open source tools into the single user-friendly platform. Now, I would like to show you how to perform the electromagnetic analysis of inductor and billet. Our problem consists of one billet made from steel and one copper inductor. This copper inductor has 8 hollow windings. To simulate this problem, we first have to create two-dimensional axis and plane symmetric geometry. Then we will generate an export mesh or electromagnetic solver called getDP. Then we will define time harmonic problem and define boundary conditions for it. Next, we will run the simulation, and finally we will post-process our results. This tutorial will be divided in 4 parts. First part will cover creation of geometry. Second part will cover generating mesh and exporting it to electromagnetic solver. The third part will be related with defining our electromagnetic problem. And finally, the last fourth part will cover post-processing results. So let's begin with the first step. We start with clean CENOS case and add preprocessor. We select geometry and mesh, and when we click on play button, then Salome or preprocessor opens. In Salome, we have to select geometry model and create a new case. Now we want to create 4 points that will define an outer computational domain. The first point will be at x and y equal to 0. For the second point, we will change x to 500. For the third point, we will change y to 500. And for the last point, we will change back x to 0. We created 4 points, and now we want to connect them with lines using line construction tool. We select the first and second point, click apply. The third point, click apply. Fourth point, and the first point, apply and close. Then we select all lines and use this tool called build face to create a face for our computational domain. Next step, we want to create a geometry for billet. In reality, our billet is 400 mm long, but since our problem is symmetric, here at the bottom you can see symmetry plane, then we can simulate only half of billet, which is going to be 200 mm long, and 30 mm in radius, so that we also do not simulate a half of domain here, which is axial symmetric against this axial line here. We create 3 points for billet. The first one is going to be 200 in y direction, 30 mm in x direction, and 0 mm again in y direction for the third point. Now we will connect the 3 points with lines, the first, the second point, and the last point. When we will create partition between this line and computational domain, then computational domain will be divided into billet and all remaining domain. Next, we want to create this lower winding here on the bottom. For that, first we will create 4 points. Again, I use point construction tool, and for x coordinate, I set 48 mm. For y, I set 5 mm. For the next point, I specify x equal to 68 mm, because if we look in our sketch, then each winding is 20 mm wide. For the third point, I specify y equal to 45 mm, because each winding is 40 mm high. And for the last point, we change back x to 48 mm. So we created 4 points that define the outer corners of our winding, and now we will join those points with lines. We select the first and second point, create a line, the third point, create a line, the fourth point, and again we select the first point to create a closed line. Next step, we have to create an inner surface of our wingding. For that we create a point using point creation tool. And here is a trick. If you hold Shift button and click on this corner, then Salome provides you coordinates of this point. From our sketch we know that each wingding has walls 3 mm thick, so that to create an inner surface, inner corner here, we add 3 mm for X, which is going to be 51 mm, 3 mm for Y, and it's going to be 8 mm. The same way, I hold Shift button and click on this corner here. We add 3 mm to X and subtract 3 mm for Y. Again, holding Shift, clicking on the corner. X is going to be 65, Y is going to be 42 mm. And for the last point, I hold Shift. X is going to be 65 mm and Y is going to be 8 mm. I click Apply and Close. I join those points with lines. Although our geometry for wingding looks good, to make a better mesh, good structured mesh that can resolve skim depth, we have to define this wingding geometry, have to divide in 4 quadrangles. For that, we again use line creation tool and select outer and inner corners and connect them with lines so that our wingding is divided into domains, 4 quadrangle domains. So now I want to select all those lines here and create a partition so that we can easier manipulate with them. Of course, we could repeat all those operations for 3 remaining wingdings, but there is one tool which we can use to create 3 remaining wingdings much faster and easier. This tool is called Multitranslation. So I selected Partition and use Multitranslation tool. For that, we have to specify a direction in which we want to translate our object. This is going to be Y direction. Step is going to be 50 mm because wingdings are separated 10 mm from each other, and height of each wingding is 40 mm. And number of times which we want to translate is 4, also including the first lowest wingding. Click Apply. So you see that Salome now created 4 wingdings for us, and the next step is to create one large partition. We select all lines and computational domain and go to Operations and Partition. We click on Apply and Close. So the next step is very important. CENOS needs information from Salome what are domain names for billet, air, copper, and also for boundaries. And for that we have to create a groups. We use this new entry group, create a group tool. And first let's define a billet group. I select face here and click on billet and click on add. Then I can type the name, it's going to be billet, and click apply. So if you look in here in object browser and open this drop down for partition, you see that new group called billet was added to partition. Same way we also add groups for air. I click on air domain. Now I hold Shift button on the keyboard and click on those holes inside or upper wingdings. Then I add them, and let's call it air. Now we need to also create the groups for each individual wingding. So first I select all domains here and click Add. And as you can see that this air domain, it was also selected and we want to remove it. So we click on air domain and remove it. We call this geometry group wind1, which will be for wingding 1, and click Apply. The same way we also add wingding 2. I click Apply, I remove air domain from here and apply. Then for the third wingding, and for the last one. So you can see that we created a group for billet, for air, for the first, second, the third, and the fourth wingding. Next, we want to create a groups for boundaries. Then we go to New Entry, Group, and create a group. Here we select a lines here, and let's start with boundaries for billet. We add this boundary and we will call it billet axis. We add it to the group. Then this line here we add it and call it billet sim, which will be for symmetry plane. Next we will add group for air. This one is going to be air axis. This one is going to be air plane. Let's call it air sim for symmetry plane. Also, we need to add this boundary, outer boundary, to a group. We will call it far field. Click Apply and Close. So we created the geometry and created boundary conditions. So the next step is going to be create a mesh. And this is going to be covered in the next tutorial. Thank you.